Okay, in this video, I'd like to introduce the Fourier Transform. The Fourier Transform is a piece of mathematics which is used extensively in science and engineering. It is useful mainly because of two properties which the Fourier Transform has. The first one is that the transform is excellent at simplifying complicated mathematical expressions. This might seem a bit strange because the Fourier Transform itself is a complicated looking mathematical expression, and we'll discuss that later in greater depth. The second reason that the transform is useful is that it has a very simple and readily accessible physical interpretation, namely that it will give you the frequency components in your signal. Now, the Fourier transform is something which a lot of people will struggle. They will struggle with, and as a result they cannot fully embrace the power and usefulness of the Fourier transform. They will spend time worrying about how it's derived or what is the significance of the cosines and sines, when in fact they should be using it to discuss quantum physics or whatever else it is that they are studying at that particular time. So what I'm going to attempt to do is alleviate all of those problems and discuss things to the correct depth and introduce the correct number of topics and try and transition between different topics, namely power series, Fourier series, and then the Fourier transform itself. And hopefully at the end you will have an appreciation and an understanding of what the Fourier transform does. You will understand its power, and you will feel comfortable in using the Fourier transform in your own studies in the future. In order to convince you of this, I'd like to list the topics which I'm going to discuss at varying degrees during the coming minutes. I'm going to discuss a bottom line up front. What is the Fourier transform? I'm going to discuss basis vectors and functions, namely cosines and sines. Frequency space and frequency components. How the Fourier transform works. In other words, how do we get the frequency components? I'll discuss Euler's formula. Why we care about the Fourier transform. We will see what the Fourier transform results look like by plotting a few graphs and where it's used. I'll discuss the transition between power series, power series, the Taylor and Maclaurin series, to the Fourier series and Fourier transforms. I'll discuss sinusoids, the Fourier series and the Laplace transform. And finally, I will give you a rough derivation of the Fourier transform. In a second video to this, I will give a complete and thorough derivation, but this one will just try and motivate why in fact we can use the Fourier transform. So let's begin. The first thing I think which we must do is read the Fourier transform, and I've written it on the bottom of your screen. So to read it would be as follows. You would say a function of time is 1 over 2 pi the infinite integral of a function of frequency e to the I omega t d omega. That would be the inverse transform. And the forward Fourier transform here, f of omega is the infinite integral, there's missing a minus sign there, f of t e to the minus I omega t dt. This is of course a complicated looking expression, but it is not impenetrable by any stretch of the imagination. And in actual fact, hopefully soon enough you'll become comfortable with what it looks like, what it means, and you will be able to use it. Moving on, let's discuss the Fourier transform. Let's give you the bottom line. The Fourier transform transforms a function of one particular variable, let's say time, which of course is measured in seconds, and this will live in the time domain. It'll be transformed to a second function which lives in the frequency domain and is going to be measured in per seconds or hertz. And the second thing it does is it changes the basis of the function from whatever it was at the start to cosines and sines. Although I'm going to discuss it at greater depth in the future, I'd just like to discuss why we can use cosines and sines as a set of basis functions in the first place. Essentially, this boils down to one mathematical property of cosine and sine, namely that they are mathematically orthogonal. Now I'm sure you understand the concept of orthogonality in terms of the I hat, j hat, k hat unit vectors, or perhaps r hat, theta hat, phi hat in this spherical polar coordinate system. So those particular vectors are both mathematically and physically orthogonal, but the reason they can describe every point in space is because they are mathematically orthogonal. And since cosine and sine also satisfy this criterion, they can be used as a set of basis functions in any particular space. Now that might or we'll say that might resonate with you, or might make some sense, or it may not. So let's try a second definition, or a second bottom line. The Fourier transform does two things. The first thing it does is a domain change to the frequency domain. So it'll change your function from, let's say, small f, and then when we speak about a transformed function, we usually speak of capital F. So let's say small f, which is your original function, is one of time measured in seconds. The transformed function will be one of frequency measured in per seconds. If your initial function is one of position, or length, measured in meters, then your transformed function will be one of frequency measured in per meter. Note, of course, we can always go from the linear frequency to the angular frequency through our factor of twice pi. The second thing which the Fourier transform does is it changes your basis functions. Now, different bases shouldn't be new to you. We use, for example, I hat, j hat, k hat, or r hat, theta hat, phi hat, or r hat, theta hat, z hat, to describe the position domain. So we have different basis functions or different basis vectors, but we have the same domain. So we would talk about, these would be our normal vectors. We have spherical coordinates and we have cylindrical coordinates. So it shouldn't be new to you to express your coordinates using different basis vectors. And I'll discuss basis vectors in greater detail in the future. But my point is that we often transform using different functions or different vectors to express the same point in space. Now, of course, the Dirac delta function can also be thought of as a basis function, because the Dirac delta function can describe every single point in space. So what the Fourier transform does is it'll change whatever basis vectors or basis functions your original function is of to ones of cosines and sines, and it'll move from the time domain, say, to the frequency domain, or it'll move from the position domain, the length domain, to the frequency domain. But each time it will express your function using the basis vectors or basis functions of cosine and sine. I'd like to discuss the concept of spatial frequency quickly. It's something which sounds very difficult, but in fact isn't at all, and it's nothing new to you, but it's perhaps just a new way of describing something which you are used to in the past. Certainly, the first time somebody mentioned spatial frequency to me, I had no idea at all what they were talking about. Let's think about temporal frequency. This is the time which has passed between two different occurrences of an event. So you might say, what's the frequency of the cars passing on the road? Well, then you would count the time between the cars passing you on the road, and if it was, we'll say, periodic, then you would be able to discuss the frequency of the cars passing you at a particular point on the road. In an analogous manner, spatial frequency is the length that has passed between the two occurrences of the same thing. So basically everything that you can see around you has some sort of spatial frequency. If you look at electricity pylons, for example, or let's say trees. Say these things here represent trees. Well then, these have a certain separation. In this case, I'm drawing them reasonably periodic. So you would say that they have a certain spatial frequency. And in order to calculate the spatial frequency, of course, you would need the distance between 2 points, or in this case, two particular trees. Of course, you could, in this case, double the spatial frequency if you halved the distance between the trees. So let's say I'm going to draw a straight line rather than a tree. So what I'm drawing now would approximately have double the spatial frequency than this particular set of objects. And finally, if we were to once again half the space between what these objects are spaced, well, once again we would be doubling the spatial frequency. So this set of objects has twice the spatial frequency of these set of objects, and this set of objects here has twice the spatial frequency of this set of objects. I find a good way to think about spatial frequency is in terms of the seats in a, let's say, a football stadium. The seats in a football stadium are all separated periodically. Let's say there's a centimetre or two between the seats, and you could say that there is a certain spatial frequency associated with the seats in your football stadium. And I'm sure at this point you're saying, well, how does it do that? How does it change using the Fourier transform to represent the function using cosines and sines and in the frequency domain? So I like to begin motivating this and later actually show why this is the case. The next question we must address is, how does the Fourier transform work? In order to begin tackling this, I'd like to ask you, how would you work out how many cents are in €1? Well, you would divide €1 by 1 cent and you would get 100 cent. How many 8s are there in 64? You would divide 64 by 8 and find out that there are 8 8s in 64. How would you find out how many 6 Hz signals are there in your particular function, let's say of time? Would you, for example, divide your function by 6 Hz? Now, I'm suggesting that that sort of operation is what gives you the Fourier transform. You're simply dividing your signal by the frequency components, or your frequency basis vectors, frequency basis functions. And perhaps that's what's going to give us the Fourier transform. But how would we do that? How would we begin to divide a signal by a frequency? What does that even mean? Well, before I do that, I must do an important aside, and it's about Euler's formula. In this aside, we will see why in the Fourier transform integrals, it's equivalent to integrate a cosine, a single cosine, and a complex exponential e to the I theta. In order to do this, we require Euler's formula. I've derived Euler's formula in complex numbers, video 3 of 4. So if you're not familiar with Euler's formula, that video is a place to begin, or a good starting point. Euler's formula is stated here. We say that e to the I theta is equal to cosine theta plus I times the sine of theta, where I is equal to the square root of -1. Now, the Fourier transform integrals involve two particular things. The first one is infinite but even integrals. Of course, they go from -infinity to positive infinity. And they also involve products and sums of cosines and sines. Now, the products and sums of cosines and sines, using some clever trigonometric identities, can be written as a single cosine. So, as we will see later when we look at the derivation of the Fourier transform, instead of having 4 terms, namely 2 cosines multiplied together, added to 2 sines multiplied together, we can rewrite this as a single cosine of a minus b, let's say, or of course we can equivalently say that's cosine of theta. Now, I said that there were two important parts of the Fourier transform integrals. The second part, or well, the first one that I mentioned, was the fact that the integrals themselves are even. Furthermore, we note that sine theta is an odd function, and inside an even integral it will integrate to 0. So a moment ago we saw that we were able to rewrite the products and sums of cosine and sine as a single cosine, which of course is inside our infinite integral. Now, because sine itself is an odd function and will integrate to 0, what would happen if we added anyway to the cosine I multiplied by sine theta and integrate it? Well, of course, that's going to be nothing else as integrating cosine theta. So it's equivalent to integrate cos theta plus I times sine theta and just simply cosine theta. I'm sure what you can see coming and namely we're going to invoke Euler's formula. So as I said, e to the I theta is equal to cos theta plus I times the sine of theta. This means that inside the Fourier transform integrals, we can go from having a single cosine or integrating our cosine to integrating e to the I theta. So when I say theta here, by the way, I really mean cosine A minus B, which came from having cos A and cos B and sine A sine B. Of course, once again, we will see that later on when we try and derive the Fourier transform proper. The reason it's useful to go from using the trigonometric function cosine to complex exponentials is that complex exponentials are very easy to manipulate. So the point here is that e to the I theta is both a cosine and a complex sine. However, inside the Fourier transform integrals, it integrates exactly as a cosine. So now it's time to go back to our question. How many 6 Hz signals are there in our function f of t? Well, let's divide our function f of t by cosine of 6 Hz. Now we saw a minute ago that cosine, when you're using these even infinite integrals, is the same as doing cosine 6t plus I times sine of 6t, because the sine is going to integrate to 0. So we just swap it and put in e to the I 6t. But we can bring this part of the expression above the line provided we change the sign on the argument. So we have f of t multiplied by e to the minus I 6t. So what that means is that f of t multiplied by e to the minus I 6t is the same as dividing our function by cosine 6t in this particular case. But this is also only at a particular point in time. So let's extend it to all time by performing an infinite integral. And what do we get? We have the infinite integral of f of t multiplied by e to the minus I 6t dt. And I'm wondering, is this in fact the Fourier transform of f of 6? Or is this, this is the Fourier transform of it. And it turns out, of course, that that is exactly what we saw at the very start. So we're seeing that all the Fourier transform is doing is dividing our signal by the basis functions and the particular frequencies. I'll of course be more rigorous at a later stage. So why do we care about the Fourier transform in the first place? Well, physically it will tell you the frequency components of your function or signal. Most functions are composed of many different frequencies, and that's something I will discuss later. So for the moment I'd like you just to accept that. Mathematically also, it is often simpler to manipulate the function in the frequency domain rather than in the original time or space domain. So what we do is we speak of decomposing our function into its frequency components in the Fourier domain. So let's remind ourselves what the Fourier transform looks like. So we are transforming from a function of time, small f of t, to a function of frequency, capital F of omega. That's the forward Fourier transform. And of course we can go from capital F of omega to small f of t by performing the inverse Fourier transform. The point to note here is we're integrating out t in the forward transform, and we're integrating out omega in the inverse transform. So it's time now to look at some of the results of the Fourier transform. Let's say that our original signal is simply a sinusoid, so it's sine 6 or 20x is written here. Note, by the way, where I'm after getting these, this isn't my work, I've just taken it from the website written there. Now if I perform the Fourier transform, I'll get a peak at a single point in the frequency space, namely at 20, which is what we'd expect because it is at 20 Hz. And the amplitude in this case is going to be 1. So for a signal sine 20x, which has one frequency, we get in the Fourier domain or the frequency domain a single point, and we get a peak of amplitude 1 in this particular case. Note, by the way, and this is very important, that this signal in the time domain is infinite in extent. You know, cosine goes from minus to positive infinity. In the frequency domain, however, it's very localized. And while I'm not going to discuss it, this is really where the Heisenberg uncertainty principle comes from. Moving on, let's add two sinusoids. So we would expect in the frequency domain to get two peaks and the peaks of the particular heights of the amplitudes. So we get a peak at 100 Hz and we get a peak at 150 Hz, which is exactly what we had up here. And note in fact that the amplitudes are also proportional, namely 1:4. So what happens if we get a slightly more complicated expression, like a square wave? Now, if we take the Fourier transform of a square wave, what we get are loads of peaks. We get lots and lots of peaks of different amplitudes, and then we get a single very large peak at a particular high frequency. The point to note here is that a square wave requires many different frequencies of many different amplitudes. Or what if we look at this one here? This is this is an exponential function, so it's, this is a bit mad here. But note that it is very localized in the time domain or the position domain, and that means it's got to be very broad in the frequency or Fourier domain. And the point here is that we're after getting a Gaussian. I'm only after plotting from x is equal to 0 forward, but of course you can spin this around the y-axis and get our Gaussian. The point to note here is that discontinuities or sharp points in space require very many frequencies in order to represent that. So I'm just giving you examples of what the Fourier transform looks like. The next thing we need to ask ourselves is, where is the Fourier transform used? Well, when we analyze the mathematics, we find out that there are what are known as Fourier transform pairs everywhere. Now, what's a Fourier transform pair? F of omega and small f of t are known as a Fourier transform pair. You could actually rewrite those two equations as a single equation, which we will see later on. And that should be pretty obvious. And they would be Fourier transform pairs. This is a Fourier transform pair, for example. Now, it's not one of well, that is a Fourier transform pair. You get a sinusoid or a cosine, and you get a single point or a delta function. So when we analyze the mathematics of different particular physical scenarios, we see that in actual fact we're getting the Fourier transform. So if you're doing quantum mechanics and you look at the position space wave function, you find that it is in actual fact a Fourier transform of the momentum space wave function. So once you see that, you can begin using all of the usual results from your Fourier analysis. Another very interesting one is that a lens performs a Fourier transform. So a lens image is the Fourier transform of the object. So a lens performs your Fourier transform. Now that's something you may have seen in the lab doing Fourier analysis, and it allows you to remove different frequency components by simply blocking points of the image. Now I'm just trying to motivate why we actually use the Fourier transform, and I'm not discussing that at greater depth. Now I would like to add some additional notes which will bring us from the beginning with power series and move to the actual derivation of the Fourier transform itself. So let's begin with power series. I'm sure you've seen in the past that a function, let's say f of x, can be written as the infinite sum, n is equal to 0 to infinity, of a sub n times x to the n. The point is here that the power series representation of a function will approximate your function locally. It will not do it globally. So you start at x, a particular point in space. Through the power series representation, you come to the function you're looking for, f of x, at that particular point. So a typical power series would look like the following. If you want to represent f of x, you would have the coefficients, the a sub n's. You have a0 x minus a to the 0 plus a sub 1 x minus a to the 1, and so on. The a just allows us to shift along the axis by a factor of a. So that should be nothing new to you. For example, if we divide 1 by 1 minus x, we get the infinite power series from n is equal to 0 to infinity of x to the n. And if you don't think that works, simply divide 1 by 1 minus x. And the trick here, by the way, just while we do it, is to add and subtract x. and later add and subtract x squared, and later add and subtract x cubed, and so on. So that's the trick in doing that, but that's for another day's work. Next, where f of x is infinitely differentiable, and also a few other things like smoothness and continuity and whatnot, we were able to extend the concept of power series representing functions to Taylor series and also Maclaurin series. So the Taylor series of a function is written here. Now that's something you can see in thermodynamics video 15 if you like, or you can see my thermodynamics videos. There's no big deal there. So for example, if you want to see the Maclaurin expansion of cosine of x, look at thermodynamics 15 and you find this particular expression. The point is we can use power series in order to represent a function at a particular point. But Taylor and Maclaurin power series expansions or approximations are only local. How do we possibly extend this to approximate a function globally? Well, Joseph Fourier proposed, and Peter, well, I'm not going to try this name, we'll say, this man showed that an infinite series of cosines and sines is able to represent a function globally. So it's something similar to a power series. My point here is that if you can accept that a power series can approximate your function locally, then you should have no particular problem in accepting that this Fourier series can approximate your function globally. Let's talk a bit more about basis functions. We usually represent arbitrary points in space using vectors. The vectors we use are I hat, j hat, k hat, and these are known as the basis vectors for your space. So because it's easier to draw in 2 dimensions, let's draw in 2 dimensions here, and we see that any point can be written or is ai hat plus bj hat, and I've written the usual properties of the basis vectors here. Now, the thing here is that in order to represent a single point in space, in say 2D space, we only require 2 basis vectors. However, we require an infinite number of basis functions. So let's say we pick cosine and sine. Well, the cos of naught is 1 and the sine of naught is naught. So we get 1 plus cos 1t and sine 2t, sine t. We have cos 2t and sine 2t, cos 3t and sine 3t, and so on up to infinity. And that is how we would represent a point in space using these basis functions. It only requires 2 basis vectors in 2D space, but it requires an infinite number of basis functions. And you might say, well, why would we bother making it so complicated? Well, like I've said in the past, it's because it allows us to get access to the frequency components of our signal, and it also allows us to later actually manipulate very complicated mathematical expressions in a manner which is unavailable using the normal basis vectors. So how do I convince you that this is the case? How do I convince you that in fact we can represent functions using cosines and sines? So I'm going to try and convince or remind you. Let's say we want to represent a square wave. We start off with a single sine wave here, so sine 1 times x. And we see that here we've sine 3x, we're after increasing the frequency. Now what if I start adding different sines of different frequencies? So I have the sine of 1 times x, 3 times x, 5 times x, 7 times x. And we get something which is starting to look like a square wave. Nonetheless, it is not a square wave. But we start adding up more and more frequencies. So adding up all the odd numbers between 1 and 15 here. All the odd numbers between 1 and 23 here. All the odd numbers between 1 and 31 here. Now before I go to the final one, I'd just like to point out that this thing here is called a Gibbs overshoot. It means that discontinuities are very difficult to represent using Fourier series and require an infinite number of terms, but that's something it's not really for this time. So finally, if we add up all the terms between 1 and 39, all the odd number terms between 1 and 39, we get pretty much a perfect square wave. Now I know that it is not perfect square wave because we have We have these areas here, but if we plotted an infinite number of terms, we would get a perfect square wave. The point is, adding up an infinite number of cosines and sines is in fact well able to represent functions. So in this particular case, in the limit sin x plus 1/3 3x plus 1/5 sin 5x plus 1/7 sin 7x is able to represent f of x, and in the limit it goes to f of x is equal to 1 on minus from 0 to pi, and minus 1 from minus pi to 2 pi. So this is in fact a 2 pi periodic function. At this point you might well be saying to yourself, well, hold up a second, why am I spending so much time working on the Fourier series? Surely it's the Fourier transform that we're here to learn about. Well, the answer is that the Fourier transform extends the concept of the Fourier series. The limits are extended from 0 as the lower limit to minus infinity, so that the Fourier transform goes from minus to positive infinity. And the Fourier transform allows us to go from discrete functions to continuous functions. So in many ways, the Fourier transform is the continuous analogue of the Fourier series. Not quite, but that is in fact a good rule of thumb. And shortly enough we will see how, starting with the definition of the Fourier series, we come to the derivation, and we work through the derivation and come to the expression for the Fourier transform. Where do we go from here? I would now like to discuss with you how we would derive the Fourier transform. And I mean this roughly because I will perform a rigorous derivation in a future video. So Joseph Fourier said that all 2 pi periodic functions can be decomposed or made up from sinusoids of varying frequencies. And we've seen that already. We looked at the square wave. And he said it using the equations which are written at the bottom of your screen. And it's something I'm sure you've seen in the past, and I'm not going to really get bogged down in them now. Now we are able to extend from 2 pi periodic functions to periodic functions of 2L using this particular form of the Fourier series. That's nothing new, I would hope. And as I've said numerous occasions at this stage, that if our function is in the time domain, t is measured in seconds, then L is measured in per second or hertz. So we are going from the time domain to the frequency domain, or the length or position domain to the frequency domain. And just in case you're wondering how do we go between cos omega t to cos kx, well, I've written down the required expressions for that. Note, by the way, we're getting back that the period is twice L, which is exactly what I wanted it to be. But this is just a quick revision of Fourier series. It's not something I want to get bogged down in. So how do we start deriving the Fourier transform? Well, let's start with the Fourier series in the time domain, and we're going to use omega instead of k. So we're going to, omega is twice pi times the linear frequency k. So what do we do now? Well, the Fourier series has already introduced, as I've said, the concepts of frequency space and cosine and sine basis functions. What we now must do is plug in for the ANs, the BNs, and A0. Now how do we get those? Well, they involve a small bit of integration, and the integrals are written here. So they're just there for completeness. So let's plug in those particular integrals and use a dummy variable inside them. Now of course they're all going to be, in actual fact, integrals of the variable t, but just for the moment I'm going to use the dummy variable r. It's just, as you'll see its usefulness later on. Now the thing is though, while the integrals of course are continuous, we still have this summation here along the cosines and sines, and the summation is in omega. We've omega sub n here, so omega is discrete. Well, what would delta omega be? If we look at it, we would see that delta omega would turn out to be pi over L. Pi over L. So what I'm going to do is, everywhere I have L, here and here, I'm going to plug in for the relevant value of delta omega. Now, I'm sure you can see what's going to happen next. As L goes to 0, here, as L goes to 0, we get something with an infinite period, or we get an aperiodic function. So, as L goes to 0, delta omega also goes to 0. And the usual things from from integrals comes in. So we get delta omega becoming d omega. We have the periodic function f sub L of t becoming the aperiodic or continuous function f of t. And we have our discrete summation becoming our continuous integral. Now it's important to note, by the way, the start point of our integral is 0. Now, all of this happened because we moved from the discrete omega to the continuous, continuous t. And we're nearly there. The A0 term, by the way, it just falls out. It's no longer required. So what we're left with is follows. We still have f of t, but this time it is a continuous f of t. There's no subscript L saying it's discrete. We have the integral, of course, from 0 to infinity. And we have our cosines and sines with respect to omega. And these, of course, are integrated with respect to the continuous variable omega. Now, you have to remember, of course, that a of omega and b of omega are the Fourier coefficients, but they in themselves involve their own integrals. Now, before we say any more, let's just remind ourselves. If we go back to the discrete Fourier series, well, b of n and a of n involve their own integrals, so this is nothing different. The a of omega and b of omega still involve particular integrals. Now, so and I'm here, by the way, in my notes here. So the a of omega and b of omega still involve the infinite integrals. Now we're able to do the trigonometric sleight of hand I was talking about earlier on. So remember, a of omega is going to have a cosine somewhere in it, b of omega is going to have a sine somewhere in it. So you have a product of cosines plus a product of sines. And the trigonometric sleight of hand I was talking about at the very start of the video allows us to rewrite this as cos of omega t minus omega r. We still have the d omega here, but because of the integrals for a of omega and b of omega, we also have a dr. And now you might be wondering, well, hold a second, where did this scaling term come from? And this is the clever part. Instead of integrating 0 to infinity, we're now integrating cosine, which is an even function. So because we have an even integral integrating an even function, we can, instead of integrating 0 to infinity, we can integrate from minus to positive infinity and just half the answer. So that's where the 2 comes from. What about the pi? Well, that was actually there all the time, even though I wasn't writing it. Because if you go back to the discrete version, we had this 1 over pi there the whole time. And that has remained there throughout this rough derivation. So it's there the whole time. Now, as I've said earlier on again, sine is an odd function, and over an even integral it will integrate to 0. So that means I could, for example, add an I times the sine of omega t minus omega r, no problem. And it wouldn't change the integral. So let's do that. And if we do that, we can invoke Euler's equation. So we have 1 over 2 pi, the double infinite integral. We have f of r as our dummy variable still there. And now we have e to the I omega outside of t minus r here. But remember that r was nothing but a dummy variable. And this is why we used it, because if I had left r as t, we would have never gotten here. It's more of this exponential sleight of hand, because the product of exponentials can be rewritten as I've done here. Minus I omega t and plus I omega t. And what we're actually looking at is our Fourier transform pair. As I said at the start of the video, we could rewrite the two equations as one. And this is what we've done. So in the middle we have our inverse transform, and on the outside we have our forward Fourier transform. Now, in regard to this 1 over 2 pi, we are always able to split that up between the forward and inverse transforms. Why? Well, because they came from the same equation in the first place. So, there are lots of different ways of writing the Fourier transform, and they are all equivalent. For example, we could leave the 1 over 2 pi in the forward Fourier transform and have only a factor of 1 in the inverse transform. We could split it up so there's a 1 over root 2 pi in both. Or what we could do is have a 1 in the forward transform and a 1 over 2 pi in the inverse transform. The final thing I'd like to say is we were doing this using omega. We can always go back to 2 pi times nu, the frequency. And if we do that, and it's quite simple using the same steps, we in actual fact don't get any scaling term, and that shouldn't surprise you, because we have a 2 pi here, and well, we actually just incorporated the 2 pi up here. And that's really all that happened. So written in front of you are 4 different ways of writing the Fourier transform, all of which are equivalent. One final point which I'd like to mention before we conclude: in order to use the Fourier transform and its inverse, you must use what are known as Fourier transform pairs. So, for example, in this particular case, small f of t and capital F of omega are known as Fourier transform pairs. And this is because, as we've seen in the past, we can rewrite both the forward and inverse transforms using a single equation, something like I have here on the top. There is usually only one corresponding f of omega for a small f of t, and that's why, like I said, they're known as a Fourier transform pair. So that's all I have to say about that. I appreciate that it has been quite a long video. However, I'd like to think that I have discussed all of the particularly important points to the relevant or in the relevant depth. So thanks for watching. Please pass this video to your friends. You might also recommend my videos to your friends. You might also subscribe to my YouTube channel and click on universityphysicstutorials.com.